Okay. Hi. Doing my module video form for the first time. So I guess I'll get started. Let's see. Come on. So I'm going to switch to my presentation. Okay, so first I'm going to start out with just describing like the difference between ANOVA and multiple regression coefficient. So we have both of them are under general linear modeling, and basically ANOVA and multiple regression coefficient are the same model, although both measure the difference that changes in an independent variable. Both measure the difference in changes of an independent variable made in a dependent variable. They differ in the test they apply to the significance of that difference. So for MRC, regression is a predictive as well as a descriptive procedure, and we're asking what are the underlying assumptions between and among variables. In the article, Gary King says regression is simply a sample estimate of a population conditional expected value. So for ANOVA, we have error being random. For MRC, we have residuals and error as being interesting. And then for ANOVA, we have F-test and T-test. F-test is just a simpler way to compare multiple level factors. So instead of doing a lot of T-tests and having alpha inflation, we can do an F-test. And then for RPT, we have a correlation between continuous and binary variables. So from RPT, we can convert it into a t-test. So first we're going to start out with MRC and its assumptions. So we're looking at assumption 1. So assumption 1 for MRC is a linear relationship between the predictor X variables and the dependent Y variables. So a rectilinear relationship between X and Y. So we're looking at studentized residuals and unstandardized predicted value. Studentized residuals are standardized with T values, while unstandardized are line of best fit values or our observed Y values. So when looking at this scatter plot, we should ideally see points being distributed along the 0 marker on a horizontal line. But as you can see, that is not what it is, but they aren't. So there's not an overall relationship between all predictors and the dependent variable. So our linearity assumption fails. We can also use this to look at homoscedasticity, and that's variability is constant across predictors. For mine, the points vary a lot. It's not really constant, so we don't have homoscedasticity, which is we ideally want it. So we have to, we fail to assume both of those. Okay, well, back to this one. For assumption, for the next assumption, we have the predictor is sensible for the outcome. So that's just, we are looking at how meaning in life, affect, and family support, how they affect life satisfaction. So we would think that meaning in life, if you have good meaning in life, you have a positive affect and good family support, then you would probably have a good relationship with life satisfaction or high life satisfaction. So that's kind of, we're looking at how these 3 variables affect life satisfaction. And then we can also look at how the prediction of Y does not require other predictors of X, and I can say that the other variables that I measured in my data set would not affect life satisfaction. So that's another one. 2 assumptions that we can successfully assume. For assumption 5, it's no measurement error. So when we look at this, Cronbach's alpha is 0.531. and that's not that high, so it's really not a great reliability. So we kind of there's kind of a little bit of measurement error in there, so it's not very good to assume. So we go to assumption 6, which is the residual equals 0. So if the mean residual is not 0, which it is 0 actually right here, but if it wasn't 0, then there's probably either overshooting or undershooting the observed value, and we don't really want to do that. So, but we have 0 here, so that's good. For our next one, we have no multicollinearity among predictors. That's assumption 7. And it doesn't look like we have any multicollinearity because there aren't really any significant correlations between our factors here. So our independent variables, there's not really like a significant correlation between them, so that's good. And then we look at our MRC with our 3 predictors. So first we can talk about parameter estimation. So that's our B's right here. And that's estimating the population parameter with sample data. So B's are the parameter estimates of the beta. And parameter estimation is basically our precursor to hypothesis testing. So we need parameter estimates to collect information for hypothesis testing. So if we want to just look real quick at our B's, this is really just how much increase can we expect in Y for every incremental increase in X. So, so if we look at that, then we have for every 1 point increase in our satisfaction with life, we could expect a 0.6068 increase in meaning in life, a 0.268 increase in family support, and a 0.069 decrease in affect. So that's pretty interesting. So if the standard error coefficients are small compared to unstandardized regression coefficient, which are our B's, then we should be more confident that similar results would come up with a larger sample as well. So our sample is only 30 people, but with a larger sample, this could be possible. And then we take a look at beta, and that's our standardized coefficients. Betas are the same as correlations, so they're right here. And Gary King says that we have to remember that correlations and causation is not the same. So our betas are basically also more difficult to interpret. They don't add any information that may compare effects from different variables, and they may add misleading information. And that's taken from Gary King's article. But yeah, so that's kind of what we have there. And then we can go back to our R-squared value, and we look at that. And we say that R-squared value is the measure of the spread of points around a regression line, our coefficient of determination, and we want a high R-squared. So mine is not high at all, so that's not that good. It's 0.051, not high. Okay. And this is just like a scatter plot of our variables, just to look at how satisfaction with life relates to our 3 independent variables, and that's just good to look at to visualize. Okay, so for ANOVA and assumptions, we have our first 3. You have a continuous dependent variable. That would be satisfaction with life because it's measured on a scale. It's continuous as opposed to categorical or binary. Our assumption 2 is that we have independent observations, and that is our between subject variables, and one person isn't in more than one factor. So we have one person for one factor out of our 4 total factors. So it's just important to have our independent observations. Our final, or an additional assumption would be categorical, and 2 levels for each. So this is for our factors, and mine is quasi-experimental. So I use which parent are you closer with, your mother or your father, that's 2 levels. And then we have where do you derive meaning in life, and career and relationships are our 2 choices for that. So both of those are categorical, and then there's 2 levels for each. For assumption 3, we have there should be no significant outliers. So box plots are our box plots here could show the outliers in these open circles here. So we would look at 9, 15, and then this one down here. And there's significant outliers for 2 box plots, so I should go back and check those and possibly throw out those data points because they could maybe skew my data or mess with it in a way that we don't want to. Okay, so for assumption 4, it's your dependent variables or our residuals should be approximately normally distributed for each cell of the design. And we can check this with our QQ tests or QQ plots for our normality, test for our normality of data. So it looks like around here, they're pretty close to our line of best fit. So that looks really good. So we could say that our normally distributed, our data is normally distributed. Okay. We can also test for this, for normality, using the Shapiro-Wilk test, and this is how we want to fail to reject the null. So for the null hypothesis, residuals are normally distributed, but we want residuals to not normally be distributed, so we want high p-values. So we can see this for 3 out of the 4. So this final one could be significant, but these 3 here are higher than significant, so we want to fail to reject the null, which we do for 3 out of the 4. And then we also have Levine's test. If it's greater than 0.05, then we meet the requirement. And this basically states that the variance of the dependent variable residual should be equal in each cell of the design. Yeah, so that kind of shows that right here. So 0.941 is greater than 0.05, so we can safely say that they're not, that they do are equal in each cell of the design. Finally, we come to our ANOVA with 2 factors, and that just states that we're just going to look at our main effects and our interactions, and looking at our main effects, which would be closeness within either parent or a median life category. Closeness in parent is significant. The mean difference between the 2 conditions. So there's a significant difference in satisfaction with life and the main effect of closeness with parent using mother and father factorial levels. Looking at meaning in life, this isn't a significant relationship. And then looking at the interaction between closeness and meaning, it's higher than 0.05, so it's not significant. And that is it for my module.